Okay, good morning, guys. So let's take a look what's happening now. Okay, so do recall we were talking about this acid bases and salt thing in the previous lesson, and we kind of stopped at here, the examples of strong alkali, weak alkali. Yes, alkali dissociate in water to give you OH minus ion. Must have dissociate, must have water, must have OH minus. Acid dissociate in water, H plus ion. Sounds familiar? We also went through the idea of strong acid, weak acid. The dissociation is partial or the dissociation is full, meaning 100% or at most 1%. So these are the ideas we went through the previous round. So today we shall continue. Actually, you all learn acid bases and salt to some extent in year 2 lah. Although it was very rushed, it was in one term. Okay, never mind, let's move on. Okay, so here there is a simple chemical test to show the difference between the strong acid and weak acid. So generally, you think strong acid, weak acid, right? Our brain will generally tell us, one faster lah, one slower. Or one more vigorous, one less vigorous. You are not wrong, you are correct. It's just that when you actually have to write out your answer, how are you gonna explain? How are you gonna show your answer clearly? So this is an example. So they can test you, but I am not those kind that they must test, but it does come out, I guess, every now and then. So this is something that you should know. So fundamentally it's not very difficult. It's a simple reaction. It's just that you need to tell me explicitly, they both have the same concentration, same volume, same this, same that. Because if you recall, experiments by right should only have one variable, like one thing that keep if everything change, then your experiment not very reliable, isn't it? So you need to tell them everything else this is the same, that is the same. And you will choose what is the reactive metal, such as magnesium, zinc. You don't just say add reactive metal, too vague lah. Yeah, that's the idea here lah. Alright, okay, next. pH. What is pH? I'm pretty sure you know what's pH, or have some inkling to what it is about. So pH is very fundamental, very basic, but it's useful too. Why? If pH more than 7, alkali lor. If pH less than 7, acidic lor. And then that's about it lor. So that's what we remember lah, generally speaking. If pH 7, neutral lor. All these are correct. Nothing wrong with everything we have said so far. The problem is students have this idea that pH tell me whether it's strong or weak acid. That is not entirely true lah. Why? What am I talking about? Okay, so you see, pH is actually a measure of the concentration. So technically, so logically, we will think, I think, try and draw a person, then the brain. Oh my god, I can't draw for nuts. But yes, so you think, I think, the strong acid is the dissociate fully thing, and the weak acid don't dissociate fully, so the ions got difference. So I think the strong acid, the pH of strong acid is lower than the pH of weak acid. So that's what you think, and I will believe so. But there is a condition here. Provided they are both same concentration and volume. If not, it is not a fair comparison. Let me give you an example of an extreme case, shall I? So let's say I have HCl versus HF. So HCl is a strong acid, HF is a weak acid. Remember I mentioned something about the strongest weak acid is only the strongest weak acid is only 1% dissociation, which is pretty little, pretty pathetic, I guess. So let's assume in this case this is 1%. Let's just put it that way. So let's say my concentration here is 0.0001 mole per dm cube. So this is actually equivalent to a pH of 4. Okay, so don't worry, you will not be asked to calculate pH. There is no formula that you learn for O level. But if you go JC, you decide to take chem, then we have formulas involved. So it's pH 4. So even though HF, what if my HF concentration is 1 mole per dm cube? So this is 1 mole per dm cube of HF. So let me adjust it a bit. So this is 1 mole, this is HCl, which means it's 0.0001 mole per dm cube of H plus, because strong acid dissociate fully ma. Weak acid, let's say 1%. Okay, sure, 1% of this is actually 0.0, don't even say 1%. Let's say this one is a 0.1% dissociation, hypothetically speaking. So 0.1% of 1 mole per dm cube is 0.001 mole per dm cube H plus. This equivalent to 3 So can a weak acid have a lower pH than strong acid? Possible. You intentionally go and play around with the numbers. So the pH is never the most accurate gauge of which is a strong acid, which is a weak acid. And in case you didn't notice, I don't like to use the word stronger acid. Stronger acid is very vague. It's comparison. I generally refer to things as either you're strong or you're weak. But within the strong, can I compare? Well, we probably can, But I like to refer to them as strong and weak. Don't you make use in very vague terms like stronger, weaker. What is stronger? What is weaker? So that makes things a little bit more complicated. Yep. So my main point here is pH. Okay, I write in red. pH is not a good indicator of which acid, or rather acid strength, the strength of the acid. pH only tell you how much H plus you have. It doesn't tell you which is stronger, which is weaker, or rather which is strong acid, which is weak acid. That's the main takeaway we have here. Alright, okay, moving on. Okay, ignore all these pages things, ignore it. So pH scale, I think is something you are very familiar with, I guess, more or less. It's just a scale. Do you memorize this scale? Not really lah. So how do you read the scale? Basically anything that's 7 is neutral, more than 7 is alkaline, less than 7 is acidic. Oh, like that lor. Yeah. Okay, so this is something, I'm not too sure whether this is new to you. So this is something you need to take note. It is in syllabus. They do test it every now and then lah. So universal indicator, when it's neutral, is green. So you need to know that it is green at 7. Then when it's alkaline, oh goodness, I see a huge problem here. This table is totally off. The color is totally wrong actually. Why? So actually weak acid right should be orange, whereas strong acid of 1 to 2 pH is red. So this is the correct color that you should be referring to. I don't understand why this is not a right color. The one I highlight on top, that is the right color. So pH 3 to 6 is weak acid, orange. Then the strong acid 1 and 2 is your red. Likewise, for pH 8 to 12 is blue. Blue for a relatively weak alkali. When it's strong alkali, right, it becomes purple. Basically the last two. So this is actually the right color to deal with. This is so weird. Okay, So universal indicator, you get to answer this kind of question in a theory question every now and then. In the lab context, we seldom use it. If you see universal indicator, I don't think you ever used it yet. Alright, okay, moving on. Okay, indicator. So this is an example of the indicators that you may encounter or you may hear before. So I think the one out of the three here, the one most relevant to you is called meter orange lah. Right? That's something you are familiar with. Then litmus, not exactly, I guess. Phenolphthalein is something that secondary school students used to use. Back in my days, I used phenolphthalein very, very frequently. But now you don't use it because it somehow becomes carcinogenic, and scientists have figured out that it's cancer causing after so many years we use it. Wow. Anyway, so you get it. So if meter orange, acidic is red, alkaline is yellow. But in the lab when we do, I thought we were supposed to stop at orange. But why got orange one? So actually that color that we stop at is actually when we have equal of the acidic form and the alkaline form, right smack in the middle. So how do you get orange? Orange is actually yellow plus red. When you have too much red, means you are acidic mah. When you have too much yellow, you are basic. So you are at the two extreme. But when you are right in the middle, when the acid just nice neutralize the base, neutral, that's where you have equal of the red and the yellow, which is orange. That's how we arrive at the color orange. Oh, cool. Yeah, that's the idea. So this question here would be a normal MCQ question, which is quite doable. In fact, this type of question when I see in exam, I'll be like, wow, yes, 3 mark, sure. Then you're wondering, how? What are you talking about? Sure, let's take a look. So for indicator P, so the sample now we talk about is water. Water is a pH of 7, isn't it? So now let's look at P. P. 7. So for P, it says that the color changes at 3. So 3 is like the midway point lah. So the real sample now is 7. So is it to the left of the midway point or the right of the midway point? Right lah, more than 7. So therefore it is yellow. So it's yellow. So, pretty easy. Yeah, that's a good thing. It's easy, good. So now Q. The midway point is 5. Sure. Our water is 7. 7 is more than 5. Is again to the right hand side, red. Okay lah, red. Cool. And the last one, you have this, sure. And the midway point is 10. Okay. So water is 7. Midway point is 10. 7 means is considered to the left the acidic form colorless, so it's colorless. So that's how I arrive at the answer of D. This is pretty easy, which is good lah. Yay. Alright. Okay, this one is in syllabus. It's just 1 mark, but they can test you every now and then. So please note down. So, you might be wondering, sulfuric acid in detergent? I thought detergent is alkali. So you must read the word very carefully. It says manufacture. So I'm not saying acid is in detergent. I'm saying that acid is needed to make the detergent. Oh, so there is a difference. Same thing. For as sulfuric acid is not in the fertilizer. Sulfuric acid is used to make fertilizer. And car battery, inside the car battery, there's really sulfuric acid. Yes. So these three are the common users, so you need to know. Yes, so this is summary lah. Your strong acid, weak acid. Strong alkali, weak alkali issue. And you have your chemical test users. Yep, that is for part 1. So now we move on to part 2. So part 2 is your solubility table, which actually technically speaking we've already done already lah. But we can quickly come back and we can quickly fill this in as a recap. I mean, it never harm to give you more right? Oxide, hydroxide, bromide, iodide. So all nitrates are soluble. All chlorides are soluble except for silver, lead. Your acronym here is probably just SL or LS, student leader or something. All sulfates are soluble except for Pb2+, Ca2+, Ba2+, or for short ClB. Carbonate is generally insoluble except for group 1, ammonium. Do recall that anything that is nitrate is soluble, don't you think? Anything that's group 1 also soluble, don't you think? Or anything that's ammonium is soluble. Oxide hydroxide is similar to the one before, or except for group 1, NH4+, and Baka, barium and calcium. So a recap, this table is quite important, but I think for practice purposes you can still refer. But maybe exam you try to memorize lah. Or rather you have to memorize. Okay, next. So these are practice questions. Huh? How? So calcium sulfate, for example. Calcium sulfate. So I look at the table. Oh, sulfate. Yay, sulfate. Calcium. Calcium is here. Oh, so this is considered insoluble. So calcium sulfate is insoluble means I write down it as CaSO4 S, because it doesn't dissolve. So that's how you can practice. So I will give you time now to practice. So you can do each question and you pause. So you refer to your own solubility table. So silver nitrate. Then you should pause now. Pause the video. Then you do. So what do? You write down the formula plus the state. If it's soluble, it's AQ. If it's not soluble, it's solid. So pause. Once you're done, resume. Oh, resume. Oh, it's AgNO3AQ. Yup, you are right. Next, iron 2 carbonate. Pause it and write the formula and the state symbol, whether it's soluble or not. Okay, again, unpause it. And you have realized that it's actually insoluble. It's FeCO3. So reminder. Ouch. Reminder is that iron 2, it is not saying that it's Fe2. Wrong. It's saying that it is Fe2+. Correct. Reminder in case you forgot. Next example, lead 2 chloride. Pause the video and write your answer. Unpause the video. PbCl2 solid. Cool. Next example, barium sulfate. Pause. Oh, unpause. And oh, it is solid insoluble as well. Cool. Ammonium carbonate. And you can pause again. You can unpause it already. So these are some examples of how you use your table to help you figure out whether it's soluble or not, lor. Cool. So far you learn about your acid plus base, give you salt and water. Yes, exactly right. So acid plus base gives you salt and water. Cool. There is a name for acid-base reactions. Acid-base reactions are commonly known as neutralization. Often students will even say the word, oh, the acid neutralized the base, which is not wrong. It's pretty true actually. So do take note, you need to know that it's called neutralization. Sometimes I'll ask you, oh, what is the name of the type of reaction here? Then you go like, acid base. Wrong. It's technically called neutralization reaction. So do be aware. Alright? Yeah, so that is your neutralization. Okay, you notice below it says ionic equation. I'm gonna leave ionic equation to the later on. I'm gonna go through the 4 reactions before I go into ionic equation. That is another difficult part. Okay, second reaction is here. Acid plus metal. Give me salt and hydrogen gas. Cool. And there is also a name here. It's actually what we call displacement. Huh? What is displacement? So very simple. Displacement. So let's break the word down, displacement. So the root word here is called displace. So you might be thinking of, oh, physics, displacement, displacement time graph. Nah, not really. I mean, also not wrong if you want to use it that way, but I think we use a chemistry explanation. So when you think of the word displace, you're like, what's displace? I don't know. What's the nearest word that we are familiar with and we are more comfortable with and is similar to displace? Oh, isn't it similar to replace? Exactly. So actually it is just replace. But there is an extra condition. So it is the more reactive element, or in this case metal, kick out the less reactive ion and replace it. So it's just replace. But but there must be a more reactive element, which I guess in some sense analogy wise is like a very big buff lot like huge gym guy. Then less reactive is as if the less reactive the smaller boy has a girlfriend, then the big guy come in, kick him up, replace him, and now together with a girl. I guess in some sense you can think of that as displacement You replace him, but you have the additional context of a more reactive metal kick out the less reactive. Oh, cool. Yeah, that's how it works. So with that in mind, how in the world am I supposed to figure out what is more reactive? So actually there is actually a metal reactivity series that you actually don't need to know now. You need to know in Tech 4. The topic of metals is key there. But so for now, if you don't want to memorize the reactivity series, which is fine, there's already so many things to memorize, right? So what you just need to know is acid do not react with silver, gold, copper. Another way to help you remember this is, silver, gold, copper, yeah, they are precious metals, but you probably won't care whether it's a precious metal. Oh, silver, gold, copper, they can all be used to make coins. Silver coin, gold coin, copper coin. So actually it doesn't really have these coin metals per se. So this is what you need to know. It can help you remember less, don't need to remember the series. So acid plus metal give you salt and hydrogen gas. Yep. So let's take a look. Gas test for hydrogen is extinguishes a lighted spin with a pop sound. I'm sure you did this in the lab. It's very memorable, which is true. So it reacts. So that's what's happening. You don't have to look at this. Actually, if you perhaps never realize, but what happened here is this. You see, your H2, the gas, reacts with the O2 and give you H2O. So actually, by right, you should actually see some condensation on the side. That's where the water is formed and condenses on that cooler surface. So actually, next time you do it, you see actually got one. Cool. Alright, next. Yep, so you have a second reaction in there, displacement and the solubility table. And let me bring you to the third equation, which is acid plus carbonate. So unfortunately or fortunately, I don't have a name for this anymore. Not every reaction I need a name. It's just that the first two is a bit specialized. We have names for it. So acid plus carbonate. So what am I supposed to get here? As this one I think you learned before. Acid plus carbonate gives me a salt plus carbon dioxide plus water. So there's no, I guess, special name to it lah. Yep, so this is the 3 reactions you learned so far. So there are 5 reactions in acid, bases, and salt, and these 5 reactions are key. They help you with, most of the reactions you deal with in exam or in chemistry is more or less backed by the 5 reactions. So it's very useful, it's very helpful. Yep, so that is what is happening. Any questions? Feel free to ask me on Teams or you can ask me in class. Just know that you can do that anytime. The Teams thing. Even if you can ask me Teams on like a Saturday 3 a.m. I won't be awoken by your text. And I mean when I wake up and I see, I'll reply you lah. So you know that you have that avenue to ask questions. Asking questions is good. So yes, we have technically finished. This is a 30-minute video, I understand, but our lesson is 1 hour 20 minutes. So I'm very sure you stop, pause, you need to revisit. So this, you will take at least almost 50 minutes or 1 hour to fully understand these examples. So just remember, we learned these 3 reactions and all these things. Alright? Actually, should I continue? Okay, I continue one last concept here. Your basicity of acid. Huh? What is basicity of acid? Are you a base or are you acid? That's so confusing. So basicity of acid is just... So I write down the terms and the examples. You will more or less be able to get it already. Monobasic acid. Dibasic acid. Monobasic acids are HCl, HNO3, dibasic acid is H2SO4. Even your CH3COOH is also a monobasic acid. So actually, I think at this point, you more or less could already figure out, they got pattern one. So I say these are monobasic, for example. So monobasic definition is actually, there is one replaceable hydrogen atom. There is 2 replaceable hydrogen atom. Another way is you can phrase it this way. One monobasic acid produces 1H+. So I'm totally ignoring strong and weak acid. there are two separate concepts actually. You have the monobasic, dibasic, and tribasic for that matter, and you have the strong and weak acid conundrum. So these two are the things that they like to test. And it's quite key lah. Dibasic means one dibasic acid produce 2H plus. Tribasic 3 lor. So that's what it means. So yeah, so with that, I will stop now. You can re-listen to certain parts of the video to help you understand better. Alright, have a good weekend, rest well, study, do what I need to do, but still de-stress. Okay.